The next speaker is Stuart Brown from UCLA.
Okay, thank you, Laszlo, and thank you, organizers, especially Sergey, who was doing so much work in preparation for this meeting. So the story I'm going to tell is pretty different than what we just heard. To my mind, it's largely inspirational in the sense that it sort of plays out in a way that you would hope that science works. The original path, though, that we were on for a couple of decades more was influenced by, some really interesting physics, and with some initial results which seemed to confirm that, the field really took off. And it took a long time to get back to where it might have been in the first place. It required a new experimental tool, which both directly and indirectly helped to correct that. Okay, sorry for the microphone. There's no one with a clip for me. Okay, so here's what I'm going to talk about. It's a story of strontium ruthenate, superconductivity in that state. And I'm going to just tell you a little bit what's interesting about that problem, and then what were the questions that remained unsettled, but nevertheless didn't deter the status quo, which was on this really interesting course. So I'll map out a timeline. And then, finally for me, a decision to revisit the problem, open questions and takeaways. Okay, so these were collaborators on the work. Up in the blue there, those are my collaborators from UCLA. They've moved on. This work was carried out in 2018, 19, and 20. I'm thankful for the collaborators in Dresden over there on the right, Cliff Hicks, Andy McKenzie, and others. Okay, so here's where it starts. A few years after the cuprates are discovered, there's another layered perovskite which exhibits superconductivity. It's very low temperature though. So from that point of view, perhaps not so interesting, but it kind of opened up a window where you could examine a system which might have a well-understood normal state. It was an ultra-clean system, stoichiometric, layered 214 material. The behavior followed the paradigm of Fermi liquid very well, at least below 30 Kelvin, and evidence for strong correlation. So the question then was, okay, in this example system from which at least we understand what the normal state looks like, what would be the nature of the superconducting state, the unconventional superconducting state that might emerge from that? Okay, and in particular, what is that superconducting state symmetry? Okay, so 1 year after the discovery, Sigris and Rice proposed that, okay, this is interesting, but maybe the superconductivity is different. That you have a quasi-two-dimensional solid-state analog to helium-3. It's exhibiting, or we expected it would have ferromagnetic spin fluctuations. Therefore, perhaps triplet pairing is a more appropriate picture that is different than cuprates. And the basis for this was similar Fermi liquid properties as helium-3 and the itinerant ferromagnetism in related materials. So they proposed some possible order parameters, which I have there at the bottom. And the second one is particularly interesting because it's a fully gapped topological state. There were then some initial experiments that really set the path. The first one was that TC was sensitive to non-magnetic disorder. Therefore, it should be an unconventional superconductor. The second one, which is the one that was really important, was the conclusion that it was an odd parity superconductor. This is based on temperature-independent night shift on passing through TC. And then finally, the third one, which seemed to seal the deal, was the evidence for a development of an internal field below TC, which would be consistent with the chiral state that would be this topological state that I mentioned on the prior slide. So here's the picture of the temperature-independent NMR. The one on the right was the first one published in '98 on the oxygen, and then confirmed in the ruthenium a little bit later. Okay, so following from that, there's a whole slew of experimental papers which would seem to line up with that. And I'm emphasizing experiments here. So the first two in red were the discovery and the proposal of the triplet order parameter. And then following that, the road to the chiral state. And the ones in bold are the ones that I just spoke about. There was also evidence from phase-sensitive squid measurements, which seemed consistent with the odd parity. This is still a loose end that persists to this day. And then finally, in the early 2010s, the report of half-quantum vortices, which would be expected for this chiral state. But somewhere in there were some worries. So for example, if you had such a state with two components, you could destabilize one of the components relative to the other. It would split the transition. One way to do that would be in a magnetic field, something like helium-3, helium-3A. In addition to that, there was a range of measurements and reports over a couple decades of low energy excitations that would not be there for the fully gapped chiral P-wave state. In 2010, there was a report of search of the edge modes that would be picked up by the scanning squid, Catherine Moeller, and that gave a null result. And then finally, evidence for Zeeman effects, the field-induced first-order phase transition of the superconducting state on going from the normal to the superconducting state. This would be something that would show up if you have a Zeeman effect, something like would occur in a singlet. Okay, so there is clearly some sociology that persists in this, and this is pointed out in Igor's nice recounting here, the inverse Occam's razor. Maybe he's going to tell us a little bit about this, but basically the idea is that, you know, if one fails to scrutinize, you end up with explanations that might be a little bit more grand than a little bit closer look would steer you to. Okay, so here comes the reset on all this. One of the proposals for destabilizing one component over the other, in addition to an in-plane magnetic field, you could strain it. And then you would enhance one of the two over the other. It would split the transition. You should see evidence for that. So this was carried out by the Dresden group, and they found this rather phenomenal behavior, which is what brought me into the problem. I mean, there's clearly a lot going on there, but there wasn't this evidence for the second transition. There was a huge change in TC, factor of 2.5, which I show there. So that was enough for me to get interested in it. But before that, even though folks had talked to me about taking a look at this problem, I shied away from it just because, well, it had been done. So why would I bother? So the device they used looks something like this. This is what our experiments look like. The picture in the middle, you can see that you've got the two clamps that are shown in Cliff Hicks device, type device, in which you have a sample in between. There's a coil wrapped around it, and of course, the crystal is inside that coil. So we could undergo these measurements with understrain, in which we would examine what's the physics of what's going on. So right away, we saw the change in night shift at TC that took place under the strained conditions. The experiment had become easier. We strained it to the place where the TC had increased to the higher value. The upper critical field is equally much higher. We were able to do our measurements at a field below the HC2, and we saw this change. So it immediately indicated that it was different than what had been proposed for the unstrained state. So initially, we thought, okay, well, maybe there's something really interesting there. There's a phase transition from what was seen at ambient conditions to the strain case. That didn't turn out to be what happened. What you see there on the left is the difference between the superconducting and normal states of one of the sites that we were picking up. So on the vertical axis is the night shift, and you can see a big change at high strain where you've increased the TC. indicative of a strong night shift, but that when you lower it, it goes away. And this turned out to be contaminated by an artifact, namely heating. And the idea is you apply an RF pulse, the heat gets out very slowly. While you are measuring the spectrum, you're measuring at the higher temperature. It's simple as that. We did some more measurements. And so just to truncate this story, we said, okay, this can't be chiral P wave. That's completely inconsistent with that explanation. We did a little bit more work and declared that it's incompatible with any of the proposed P wave order parameters. So a couple of comments about the trajectory of science. We had these results before the March meeting. We didn't report them. Why not? Because we felt it important to talk to Yoshimeno, Kenji Ishida, other authors who had years before made these different measurements. That turned out to be very fruitful. The exchanges we had were marked by, I would say, very gracious interactions. Kenji went back to the lab, redid the measurements, followed our prescription, and wrote back to me one day. I saw the email come in and I'm thinking, uh-oh, because of course, all this time I'm very nervous. Okay, we must have done something wrong. So what would it be? He says, okay, I found the same results. Very good. In addition to that, the neutron scattering measurements, which had initially found a temperature-independent spin susceptibility, also confirmed the results. So as I said, this is the way science is supposed to work. You go back to the lab, you check, you come back, it works out. Okay, so there's still some unsettled questions in this. The ground state order parameter is still not agreed upon. In particular, there's this question of two components. There is an experiment. There are a couple of them, which I highlight there, but I want to talk about the one on the bottom, evidence for a split transition, just for a second before concluding. These are MUSR results from TU Dresden in collaboration with Cliff Hicks. And what you see there is the outline of the transition temperature to the superconducting state going through the peak that I showed you earlier. And then the onset of time reversal symmetry breaking in the MUSR measurements, which seems to be basically temperature independent throughout. So the idea would be that you'd have a split transition. So I'm just going to show you another piece of data before concluding. This is from elastocaloric, which is a very sensitive quasi-thermodynamic measurement. And the colors are indicating the strength of the elastocaloric, negative or positive. And so where the white is in the middle there is either an entropy maximum or an entropy minimum, depending on whether you are in the superconducting or the normal state. But what you don't see down here is evidence for the second transition in this. So the thermodynamic measurements have been done, don't see that. That's peripheral to what we're talking about at this conference, but I did just want to mention that there is an issue there. So what are my takeaways? It took a long time to reset the path for this. And the reason it happened, I think, is that there was this new tool. There was this new opportunity. It led to some results that looked interesting. Me and others kind of followed up on it. And in our case, we could show that the chiral P wave just couldn't be. I will say, Thomas, thank you. There was enough interest that when I wrote this into the proposal that this is what we want to do, that the CMP program could support it. I'm not sure if there wasn't a new tool, whether it would have been received the same way. The participants in the inquiry here were scientifically thorough in following up and personally gracious, I would say. Maybe this was influenced by the fact that, at least the way I look at it, is that the results that we were presenting were bulletproof. We didn't try to overstate our findings. We just laid out what we did and how we could account for what had happened before. And then the number 4 is kind of gratuitous for this meeting, but I put it there anyway. Okay, so that was a short recount, but anyway, thank you very much.
Thank you very much, Stuart, for this very clear presentation. First comment, question.
Yeah, that's also a comment, not a question. I think that I disagree with you saying that this is how science should work and that everything was in an ideal way. I do agree that the field was blessed with main player, even though maybe not 100%, but the main player were honest, scientifically qualified people who, if they were making mistakes, that was very honest and understandable mistake. But I think that the problem here was that the field was dominating by two absolutely outstanding scientists, Yoshi and Manfred, who were completely blinded by the perspective of triplet superconductivity. They were signals much stronger than how you outlined them long before. And you didn't mention, but we had a PRL in 2005 where we analyzed all experiments and we showed that the only really beyond reasonable doubt proof is NMR. And we also pointed out that there were internal inconsistencies. We didn't know why, but we pointed out that something was wrong with NMR experiments. That was the easiest PRL in my entire life. It went through 3 reviewers, and I could see that they were all 3 were elated that somebody dared to raise voice against triplet superactivity. Many people had doubts, but we were afraid because such great people said that this triplet, that this must be triplet. That, I think, is the biggest problem. I think that should be addressed, and somebody like you, Stuart, should have come back in 2005 and check again. And you didn't, and Yoshi didn't, nobody didn't until you stumble upon that purely experimentally. And I think that's something that we should think about, how to avoid these situations in the future.
Point taken. Apologies for overlooking the paper. I stuck to the experimental papers, if you notice here, except for the original proposal. But yeah, your point well taken.
I don't have an explanation except that what I said, there is, it's a lot of work to go to sort of dive into a problem, and much time has to be invested. And then, so I also heard these questions, maybe following the article, for years, and just never dived into it because there wasn't some new angle.
And so, maybe that's partly the sociology of it too, that I'm guilty of. But, that's what it took, right? There was this, really interesting change of TC. So, okay, there's something to go after here. Let's try it.
Stuart, as Andy McKenzie has shown, that the material is very sensitive to disorder. There is no sample dependence in the different data.
Well, there was a lot of work over years to develop what I guess Yoshi and others might consider to be the best crystals, and they all have the TC kind of saturating out at around 1.5 Kelvin without any improvement above that. Mean free paths are very long. The quantum oscillations are well defined. Yeah.
Thanks for a great talk. Do you have some comments on the half quantum vortex experiments? I don't know if you looked at that again, or is there a problem there?
Yeah, I mean, those are nice experiments. I mean, there are ways out, and so those were, I think, brought up in the intervening years. For example, if the flux doesn't thread through, the whole of the microcrystal, but passes through a wall, for example. I mean, it is, I suppose it's possible, just on the surface of it. They're very anisotropic, and
yeah, I was a co-author on that paper, so let me comment on that. So we actually asked Rafi to turn the sample and thread it again, to the field, because the sample was square by itself, and he turned it by 45 degrees and he saw the same half steps. So we were kind of puzzled, so no way you can explain it by the wall threading if you break the symmetry like that. So I'm still puzzled what's the result.
Further questions?
Let's see. I guess I could add one more thing, which I wasn't thinking of, which is that, one can construct two-component order parameters, superconductors, which give the half flux quantum. Steve Kivelson wrote about it a couple of years ago with his students. So I don't know if that's the explanation, but there are other proposals there.
I have a question, not so much about the specific science, but rather about the data. I'm at the University of Pittsburgh, and I'm responsible for designing the systems we're going to use to store our data. And given the last talk and this talk, I'm starting to lay down a few requirements. So this sounds like we need to be able to store data for at least 15 years, if not longer. And the last talk said we needed to be able to store a bunch of raw data. I was wondering, if you were in my shoes, what are some of the requirements that you might lay down?
I rather liked what James described. I mean, he's clearly thought about this a lot more than I have. I mean, I do think that the trends are all in the right direction, where for the papers that we publish, that they are available in our repository. And I guess the important thing there is to make sure that the repository stays unbroken, right? That is always accessible.
There are no more questions. Let's move forward. Thank you very much once again.